Okay, we're going to work through a video here where we talk about the electromagnetic spectrum. Um, this is one I pulled off of this particular website. You can find a variety of these with different information, but it'll have the same concept. Um, this particular one, it starts out with gamma rays on the far left and works its way down in energy to radio waves over on the right. So you're going from high energy forms of waves to low energy forms. Electromagnetic radiation is just like a fancy word for light. So these are like different wavelengths of light, um, and you probably heard of most of them. There's only a certain little sliver of light that you can detect with your eyeball, and that would be this visible spectrum right here. The other ones require the use of some type of instrument to be able to pick them up and use those particular wavelengths or frequencies. So this visible portion, um, that you might say, oh, that looks like a rainbow. Over here you have violet, and which is right next to ultraviolet. And it works its way down in energy down to red. So you might recognize those as the colors of the rainbow, or if you've ever seen white light scattered, separated into its component colors using a prism. So we'll work using this to identify certain types of light, and when we do some mathematical calculations, you'll be able to determine if that's something you could see with your eye or if you needed an instrument to do it with. And I don't know why I just made a squiggly mark, but I can undo that. But and then at the bottom here, I have another picture from your textbook where it may be difficult for you to see the picture on here, but one thing that it talks about is wavelength, which is simply the distance from the crest of one wave to the crest of the next wave, and it's represented by the Greek letter lambda, which is like a baby lamb, like lamb, and then duh. And it looks like an upside down Y, sort of. Um, and wavelength is measured, there are lots of different length units, but for mathematical calculations, we measure or convert to meters. So that's very important to be able to convert different units, to meters to do the math. The other term that's introduced in this part is frequency, which is pretty much exactly like it sounds like it would be. It's how many of these waves pass a given point in a second. So this certain distance, the time is 1 second. If you're looking at the cycles per second, that's its frequency. Frequency is denoted by the Greek letter nu, N-U, which kind of looks like a V, sort of. And since it's per second, it's often given the units like that, which that just means when you see that, you just say per second, which is also equivalent to a hertz, H-Z, big H, little z. So per second is the same thing as hertz. You have to be able to convert from hertz or from some other unit like megahertz to regular, hertz, base unit hertz, to do the math with. So you can see the first picture. It says 3 cycles per second, or 3 hertz, or 6 cycles per second, or 6 hertz, or 12 cycles per second, or 12 hertz. So you can see as the wavelength decreases, gets shorter, then the frequency increases. So that's an important relationship to make from this. So as wavelengths decreases. So decrease in lambda will correspond to an increase in nu, or frequency. So that's just, you need to make that relationship early on, and this picture kind of helps you do that. This one over here, it discusses amplitude, which is pretty much the height of the wave. An amplitude is either it's like this is marked like halfway through the wave, so that distance is an amplitude. You could also say it's from there down to a trough. So the top of a wave is called a crest, the bottom is called a trough. An amplitude is the distance from an equilibrium position, a rest position if you call it that, to the crest or to a trough. Or it's 1/2 of the distance of the entire thing. So whatever 1/2 of that is an amplitude. So you could equate amplitude with, one example might be if you're listening to your radio and your jam comes on and you crank it up a little bit, you have increased the amplitude, the energy being carried by that wave, kind of. So amplitude is kind of a reflection of energy that's being carried. The higher the amplitude, the louder it is, so, or something like that. So, you know, when your favorite song comes on, you're adjusting the amplitude when you crank it up a little bit. So we're going to take these two concepts, these two terms, frequency and wavelength, and we're going to do some mathematical calculations with those, and hopefully you'll be able to do those on your own after you see a couple of examples. So let's go ahead and dive into an example. So here's one that says a part of the electromagnetic spectrum has a frequency of 6.20 times 10 to the 13th hertz, or per second, or cycles per second. So this is the same thing as big H, little z. So you know what its frequency is in the problem. So now all you need is some kind of mathematical relationship that relates your nu, which I tried to write right there, your frequency to your wavelength, your lambda. Well, we do have a mathematical relationship for that. So in order to do that kind of calculation, we need to know how fast the light is moving. So the speed of light is a good place to start. So the speed of light in a vacuum is constant. So c is the speed of light in a vacuum. It could be the speed of light elsewhere, but we're going to primarily work with nothing to interfere with the speed of the light. So there's nothing for it to pass through. There's no medium. And we'll work with a certain value, and that value from your textbook is 2.998 times 10 to the 8th meters per second. So it is very important that you use meters per second so that you can use per second and come out with a wavelength in meters. So we'll use that value, and we derive this formula. You'll use this. Speed of light is equal to the wavelength times the frequency. So that's pretty simple, straightforward formula. If you like formula triangles, you want to put it in there. Since we're not always just solving for, c, lambda times nu will give you speed of light. So in this particular problem, you have a frequency that's given, and you're going to work off of this speed of light. So if you look at your formula, if you want to solve for wavelength, you have c over nu. So that's your formula, c over nu. And you can make the other arrangement as well. So if you wanted to solve for nu, you have c over lambda. So in this problem, you end up take your numbers now. You got 2.998 times 10 to the 8th meters per second. And you're going to divide that by 6.20 times 10 to the 13th hertz, or per second, if you want to write it that way. And then you'll notice what's going to happen is the per second part will get removed right there. So it will take care of each other, and your unit left over is the meter, which is a unit for length. And if it says no other thing up here about what unit to report it in, calculate the wavelength, you should probably do that in meters. If it does not say. If it asks for a certain unit, then you need to get this meters and convert it to that unit. So when you do your math for this one, you're solving your particular problem. You have the top part here, and you're going to divide that by your bottom portion there with which is your frequency, and you're going to get your lambda, and you're only going to get to report 3 significant digits because this had 3 significant digits. That was available to 4, but you're limited by that. So you're looking at 4.84 times 10 to the minus 6 meters. So there is your wavelength. So if you look back at your particular, your chart, you'll notice that that's somewhere in this is either 10 to the minus 7. So it's somewhere in here. I would say that one's going to be in the infrared region. So so you can look at your wavelength to see what, if you wanted to try to guess what kind of radiation that was. Infrared radiation would probably be if you had to answer it. It doesn't say that you had to here, but it would be a good idea for you to be able to look at a chart like you could have access to, and determine what type of radiation you're looking at simply based on that calculated wavelength. We'll take a look at another one here. Calculate the wavelength of light in nanometers. So in this problem, they're asking for the wavelength again, but this time in a different unit. So when we get our answer that's going to come out in meters, we need to make sure that we convert it to report our answer in the requested unit. So we're going to do the same thing that we did before. We already know that from the previous equation that the wavelength is C over nu. Also, you can look at this rearrangement of the equation and remember the relationship between wavelength and frequency was they had an inverse relationship. If one went up, the other went down. So if wavelength went down, frequency went up, or you can say the same thing. Frequency goes up, wavelength goes down. They have opposite effect on each other because you're dividing them into the speed of light here. So if that's a bigger number, if frequency goes up, then wavelength is going to go down because you're dividing by a bigger number. Anyway, so back to this one. We have our frequency right there given to us. So we're going to use our 2.998 times 10 to the 8th meters per second. And we're going to divide that by your 1.26 times 10 to the 15th per second, or hertz. And then again, you're going to be limited to 3 significant digits when you do that math. So when you do this division, your per second part cancels out. You're going to round that to 2.38 times 10 to the minus 7 meters. So you have your answer in meters, and then it says convert it to nanometers. So you have to do a conversion step after that. So 1 nanometer is 1 times 10 to the minus 9 meters. So this step will take care of that, cancel out your meters. Take this, divide it by 10 to the minus 9, and you're going to report 238 nanometers as your answer. You don't have to write that in scientific notation, but if you did, it would be 2.38 times 10 to the second nanometers. Same value, just if you decided to write it in scientific notation. But that number, 238 nanometers, not necessary for you to, write that out. So this particular answer, 238 nanometers, either way, okay? So that'll take care of that one. And again, you could look back at your, I guess your particular diagram. If you were looking at the meters portion right here, 10 to the minus 7, and if you wanted to see like what type of light that was, what type of radiation, you could scroll back to my picture, 10 to the minus 7. Well, so it's a little bit shy over here of being 4 times 10 to the minus 7. So if we had to move on over, because your eyes can only really detect like from 4.0 times 10 to the minus 7 to 7 times 10 to the minus 7. If you get a wavelength that's shorter than that or longer than that, your eyes don't pick it up. So if I had to take a guess on what that would be, I would say it's just on the other side of violet and probably ultraviolet. So if I had to guess, I would say that would be UV. So if you've heard of UV radiation before, that's about what you're looking at. So we'll do another one. On this one, we're going to use a different diagram. So this particular one is applying Bohr's atomic model. Calculate the wavelength of the radiation emitted when an electron in a hydrogen atom makes a transition from the 5th energy level to the 2nd energy level. So, and then quantify in energy. So we're going to learn a new equation for this part. This first part is not that difficult if you have an available resource. So if you do have access to a copy of the for reference material, the Bohr model for the hydrogen atom. This is when we're talking about energy changes and wavelengths of photons, the wavelength of light that comes as a hydrogen's electron moves from higher energy back down to a lower energy level. So these are all emission wavelengths of emission of light. So the electron is losing energy and falling back down. So something happened, it went up in energy and then fell back down. And when it does, it emits light. And that light, depending on where it fell from and where it fell to, has a specific wavelength. And then these lines, as you can kind of trace them down to be able to figure out what your wavelengths are. So the question that you had was from 5 to 2, 5th to 2nd. So if you go look at a picture like that, well, this is your n equals 5 right here. So if you're going down through here and you locate an electron in the 5th and you want it to go down to the 2nd, right? So 5 to 2, when you follow that line, you have a wavelength that's given. So this is wavelength in nanometers. So this is 434 nanometers for your wavelength. So you just can trace that line from 5 to 2 and see what its wavelength is. And you can see that that's in the visible spectrum right there. So that has a name called the Balmer series, where it falls down to the second energy level. When hydrogen's electron goes back to the first energy level, n equals 1, then it emits a UV, which you wouldn't notice that with your eyes, but and also if it falls down to the n equals 3 from a higher energy level, then it's in the infrared spectrum. So anyway, so we know what our wavelength is, 434 nanometers. So I'm going to go back to my question, 434 nanometers. Now it doesn't say to report that in nanometers. It says calculate the wavelength. So I don't know that that's going to do me any good until I put it back into the accepted unit for that to do the math with, because the next portion you're going to need an equation. So we're going to go ahead and just do a conversion just for future use. So we're going to change nanometers to meters. So 1 meter is 1 times 10 to the 9 nanometers. Or, you could just as easily write that as this is really the way I like to do it. 1 nanometer is 1 times 10 to the minus 9 meters, because the prefix nano means 10 to the minus 9. Then this will let you cancel out your nanometers, and then you're going to report that as 4.34 times 10 to the minus 7 meters. And that way you have a unit in meters. And then we're going to learn about a new equation. So Planck's energy equation is what we're going to learn about here. And we're going to work it. We're going to use a couple rearrangements of the formula just to learn a little bit how to make the work go easier. So the first way that you'll see Planck's energy equation written is E as in energy. So energy equals, well, there's a constant called Planck's constant, which is represented by the letter H, and multiply Planck's constant by the frequency in hertz. So that's my formula, and you already have another formula as well. Remember you had C equals lambda nu, and we rearranged that to solve for wavelength earlier. We can also rearrange that to solve for frequency. So frequency is C over lambda. So nu is C over lambda in this equation. And here you have energy is H times nu, or Planck's constant times frequency. Then one other way to write this is to, in place of that nu, you can also say that E is equal to, replacing this nu with this right here. So E equals HC over lambda. Well, the reason you might want to use this one is because you just solved for a lambda. Okay, so this, we know speed of light is a constant value. Well, Planck's constant is a constant value. So if I give you the value for Planck's constant, and it's always that number in those units, then at the top, that number, these two are constants, and if you're given a wavelength or you solve for one, you can solve for energy. So the value for Planck's constant, right, so H equals, well, it's 6.626 times 10 to the negative 34, and the joule times the second is the unit, joule seconds. So Planck's constant has this value, and since you're working with two constants, you can actually simplify this if you have a wavelength to use, you can simplify this right here a little bit. So what you're doing is, unit-wise, you're multiplying Planck's constant times the speed of light. So what that looks like is, for units, you got Planck's constant, which is in joule seconds, and you're multiplying that times speed of light, which is meters per second. So you really have joule seconds multiplied by meters per second, and your second and per second cancel out, because a second divided by a second is just 1, so it goes away. So your unit on the top is going to be a joule meter, joules times meters. So now all you have to do is put a number in front of that. So the way you do that, just multiply this value times the speed of light, and you get to have 6.626 times 10 to the minus 34, and you multiplying that by 2.998 times 10 to the 8th, and that is going to be always right here. And you're going to get 4 sig figs, because each one of those you have given to 4. So your answer, or your top portion, is 1.986 times 10 to the negative 25 joule meters over wavelength in meters. So this will allow you to solve for any problem that you have to calculate energy given a wavelength. So if you're not given a straight up frequency, then you can use this equation, and this top part, if you're working with the speed of light and Planck's constant on top, well, that value is right there. So your energy is equal to 1.986 times 10 to the minus 25 joule meters over your wavelength in meters, which is 4.34 times 10 to the minus 7 meters. And now you have a top and bottom meter unit that'll cancel out. And then when you divide that you divide your constant values up at the top by your 4.34 times 10 to the minus 7. Then you have to round that to 3 significant digits because of your 4.34, and you would get 4.58 times 10 to the minus 19. Your unit is joules. And then one last thing, since it says energy is being released, one way that we denote that is we put a negative in front of it like that. So this says that this is showing that this much energy is being released, with a negative sign there, being released. The joules, that's the SI unit for energy. So there are other units to measure energy in, but the joule is the unit that this is going to come out in. So those kind of problems you can work through and practice. You can do different energy transitions based on your a picture. So you could take your reference material picture and look at each transition, look at the wavelengths that you have in nanometers, and you could convert that to meters, and then you could do the energy transition for those as you work through it. Now on this particular one, we have to solve for wavelength given a frequency, but our frequency is not given in regular hertz at first. It's given in a prefixed unit, megahertz. So this is typical of radio station broadcasts. If you've turned your radio on, that number, whatever your favorite radio station is on a regular FM radio dial, that unit, that number has a unit on it of megahertz. So if you like, you know, KZ 106, which is 106.5 megahertz, or this one is the local radio station, where I live, 102.7 megahertz. If I want to calculate the wavelength in meters, I have to do the same formula that we did before, which was lambda equals the speed of light over the frequency, but the frequency has to be in hertz. It can't be in megahertz. So when I work through this problem, before I start doing the math, my first step is going to be a conversion. So I need to convert the 102.7 megahertz to regular hertz. So, well, the prefix mega, 1 megahertz, is 1 times 10 to the 6th hertz. So the prefix mega means like million. So there's a million hertz in 1 megahertz. But this way you can cancel out your megahertz and get this to come out in just regular hertz. So, when you do your calculator part of this, you basically end up with scientific notation of 1.027 times 10 to the 8th hertz. So that's your frequency in hertz. You don't want to do the math with 102.7 like that. You need to convert it to hertz. So this is the same amount, the same frequency as this, only reported in a different unit. And you need it to be this one so it'll work out for you, because remember, a hertz is the same thing as per second. So when you're doing this problem, your lambda equals, well, your speed of light, 2.998 times 10 to the 8th meters per second, divided by 1.027 times 10 to the 8th per second.